Question 9 is asking you explain the effect of activation energy and enthalpy on the position of equilibrium of a reversible reaction. So this is also one of the syllabus dot points that gets neglected a lot. And it's related a little bit to question 8. Because in question 8, we said the one where activation energy barrier is similar is the one where it's likely to be reversible, right?
Yeah.
And then we also said if it's going to be irreversible, then it's going to favor the reaction with the lower activation energy barrier. So that's basically what we're doing in question 9, just putting that down into words. So now this question's not asking you if it's reversible or irreversible, though. It's asking you for if the reaction is already reversible, where is the position of equilibrium going to lie?
Okay.
So we said if the activation energy of one side is lower than the other, it's going to prefer that side, which basically means the position of equilibrium is slightly shifted towards that side.
Yeah.
So 4 marks, 2 concepts, activation energy and enthalpy. So what we'll do is we have 2 paragraphs. Paragraph 1 on activation energy, paragraph 2 on enthalpy, and then we're going to start it with the definitions. The activation energy barrier is the minimum kinetic energy reacting particles need to have. Particles need to have to form products. And then we said, so the lower the activation energy barrier, the easier it is to overcome and cause a reaction, which means the position of equilibrium favors the reaction with the lower EA.
Yeah.
Now, just keep in mind that let's say you have a reaction, reactants turning into products. If the forward reaction has a lower activation energy barrier, what that means is that it actually prefers shifting to the right. So the position of equilibrium is on the right-hand side.
Yeah.
Yeah, because sometimes we think of forward reaction and we're like, oh, yes, you are starting at the left, but it means over time you're going to the right.
Yeah.
And then if the activation energy barrier of the reverse reaction is lower, then it's actually going to the left and it's going to favor the left-hand side.
Yeah.
Favoring the left-hand side is not the same as favoring the forward reaction. Favoring the left-hand side means you went from right to left, which means you favored the reverse.
Yeah.
Yeah, so that's activation energy. And then the thing is, activation energy and delta H are very closely related together because if you draw the energy profile diagram for a forward and reverse reaction, you can see how the talk we had about activation energy links to the enthalpy. So let's say we're doing delta H, and this is 0, this is pathway. The energy profile diagrams have to be opposites of each other because we're doing forward and reverse. So the reactants and products swap. So let's say, I don't know, let's say the forward reaction is exo, which means it's losing energy over time. So this is what it looks like.
Yeah.
And then this is the activation energy. And then for your reverse, products become reactants, reactants become products, and then the activated complex stays the same. This is endo, and this is activation energy.
Yeah.
So what do you notice about the activation energy of the exo and of the endo reaction?
For the endo, it requires like more.
Yeah, so if you draw equal and opposite energy profile diagrams for a reversible reaction, then the endothermic reaction always has the higher activation energy barrier. So then your answer to part B is going to be endo reactions have positive delta H, exo reactions have negative delta H, and activation G of endo reactions is higher. So then you combine your second paragraph with your first. Activation energy of endo reactions is higher. Activation energy of exo reactions lower. We said earlier that the lower the activation energy, the more it prefers that side. So if the activation energy of the exo reaction is lower, then it's going to favor the exo reaction,
Yeah.
which means the position of equilibrium favors the delta H less than 0.
Okay, yeah.
Yeah. So now that you know this is the most standard question taken directly out of the syllabus. Just keep in mind the question can be worded differently in the future now. They've asked you for the effect of activation energy and enthalpy. There might be a question in your exam that's given you a particular equation and they've given you the enthalpy in the equation. And then out of nowhere, they ask you, oh, predict where the position of equilibrium is. And then you're like, I don't remember studying how to predict the position of equilibrium. You haven't. You haven't done predicting the position of equilibrium, but you have done the effect of enthalpy on the position of equilibrium. So if they gave you an equation and they gave you a delta H, that's enough for you to know where the position of equilibrium would be.
Okay, yeah.
Yeah. So based on what we've said here, let's say they do give you an equation in the exam and they're like A plus B turns into C plus D, and then delta H is plus 56. Plus
Yeah.
56 means the forward reaction is endo.
Yeah.
We said, based on what we've talked about here, that the endo reaction has the higher activation energy,
Yeah.
which means it's harder to do. Which means if the forward is plus 56, the reverse is minus 56, which means the reverse is exo.
Yeah.
And then we said reverse being exo has the lower activation energy, which means it's easier to occur. So the reverse is going right to left. Your prediction is going to be the position of equilibrium lies on the left-hand side,
Yeah.
slightly on the left.
Yeah.
Make sense?
Yeah. I
Yeah.
love
So just, huh?
understand. I love when I understand stuff.
Yeah. Yeah. Yeah, me too, me too. I love it too. Um, yeah, that's good though.
Mm.
So just keep in mind when you go to do your exam questions, try to think of the different ways that this kind of stuff can show up. Yeah. And it doesn't require a lot of creativity to do that. It just requires reflection on how you've seen the different pieces of information. So for example, if you see a question worded once that specifically mentions enthalpy, they might next time give you the energy profile diagram.
Okay, yeah.
They might next time give you the equation with the delta H.
Yeah.
They might next time not even ask you in part A. Part A might be a calorimetry question where you have to calculate enthalpy yourself, and then part B asks you to predict the position of equilibrium.
Okay, yeah.
Um, what else could it be? Or it might even be we say generally that if it's a decomposition reaction, it tends to be endo, and if it's a synthesis reaction, it tends to be exo. Because decomposition is when you're breaking stuff up, you need to absorb energy to do that. So that tends to be endo, and then synthesis is the opposite. So if decomposition is endo, then synthesis is exo. So
Okay.
if there's this general rule, they might even give you an equation without giving you the delta H.
Okay, yeah.
So if you can identify that it's a decomposition, then delta H is always going to be negative.
Yeah.
And then keep in mind with certain equations, we always know if it's exothermic or endothermic. Neutralization is always exo, combustion is always exo, in which case for those ones, they might not give you the enthalpy as well.
Yeah.
But then they might ask you for the position of equilibrium anyway. Yeah. So as you're doing your questions, brainstorm how many different ways you've seen certain pieces of information, and that might be how they show it in the exam.
Okay, yeah.
Any questions?
No.
All right. Question 10, write the equilibrium expression for the following equations. It's concentration of products over reactants to the power of the coefficients, excluding any pure solids or any pure liquids. What would your equilibrium expression for A be?
NH3 squared on N2 NH2 cubed.
Yep. B.
CO squared O2 on CO2 squared.
Good. C.
H3O plus HCO3 on H2CO3.
HCO3 minus on H2CO3,
Yeah.
none of the H2O because that's a pure liquid. D.
H2O to the power of 4 on H2 to the power of 4.
Yes, none of the iron and none of the iron Fe3O4 because those are pure solids. E.
Cu plus on Zn2 plus.
Yes. Okay, good. The following reaction takes place in a sealed container. 4NH3G plus 3O2G turns into 2N2G plus 6H2O, and delta H is less than 0. Explain how its increase in temperature affects the value of the equilibrium constant for the reaction. This is a Le Chatelier's principle. Before we go to the equilibrium constant, sorry, we have to remember that the equilibrium constant is concentration of products over concentration of reactants. So if we do want to link it to the equilibrium constant, then we have to talk about how it shifts to the side with more products or shift to the side with more reactants.
Yeah.
When we identify a Le Chatelier's principle question, we tend to have to talk about it pretty much everywhere throughout our response. So when we identify it, it's always good to just define it straight away at the start. So your definition of define LCP first, Le Chatelier's principle says that when a disturbance is imposed on a system at equilibrium, the system will shift to oppose the change.
Yeah.
That's the formal definition. And then the change here is you start at the increase in temperature and talk about how the system tries to bring the temperature back down. So let's go, when we increase temperature, according to LCP, the system will want to decrease temperature.
Yeah.
And then we have to talk about how it does that. When we decrease temperature, are we trying to release more heat or are we trying to absorb and take the heat away?
Absorb the heat.
Yeah, we're trying to absorb the excess heat added. Which reaction does that? Does the endothermic reaction do that or does the exo?
The endo.
Endo. So the system will favor the endo reaction that does this, which is why the question had to give you the enthalpy. So based on the equation and the delta H given, is the endothermic reaction the forward reaction or the reverse reaction?
The reverse.
The reverse. So the endothermic reaction is gonna, which is the reverse reaction, which has the delta H positive. So if it's the reverse reaction, do we go right to left or left to right for the reverse reaction?
Right to left.
Right to left. So the position of equilibrium shifts from right to left, which means what's happening to the different concentrations? Reactant concentrations are,
Increasing.
and then product concentrations are
Decreasing.
decreasing. And then we know that the equilibrium constant is products over reactants. So if reactants are increasing and products are decreasing, what's happening to the equilibrium constant?
It's becoming smaller.
Yes, so there's going to be a smaller K value, and that's your answer.
Okay, yeah.
Any questions?
No.
All right. Question 12. Nitrogen dioxide is produced from a reaction of nitrogen gas and oxygen gas. The reaction is reversible and exothermic. A, write a balanced chemical equation for the reaction. Nitrogen dioxide is produced from. a reaction of nitrogen gas and oxygen gas. Nitrogen dioxide is produced, which means it shows up on the right-hand side of your arrow. So reaction of nitrogen and oxygen means nitrogen and oxygen are on the left. So read the question carefully because it might not mention it in the correct order. Nitrogen first, then oxygen after. They told you that it's reversible. So use a double arrow. What's the formula for nitrogen dioxide?
NO2.
NO2G. And they told me to balance it. How do I balance this?
2 in front of NO2. And then 2 in front of O2.
Yes. And then and that's pretty much it, but they also told me it's exothermic, so I'm gonna add a little bit of extra detail and say delta H is less than 0.
Yeah.
Part B, write the equilibrium expression for the reaction. What's the equilibrium expression?
NO2 squared on N2 and then O2 squared.
Yes. And then part C, identify the change the equilibrium constant when pressure is decreased, assuming all other conditions are constant. This only asks you to identify the change, so we don't have to talk about LCP, but we'll make the notes anyway, because you can't really identify the change without talking about it. So if we decrease pressure, according to LCP, the system just wants to do the opposite and the system's going to want to increase pressure. Pressure is exerted by gases. So for you to increase pressure, you need more gases.
Yeah.
So how many gases are on the left-hand side?
3.
3. How many gases on the right?
2.
2. So if the system wants to increase pressure, which way is it going to shift?
The left.
Yes, the system will shift to the left, which has more moles of gas. And shifting to the left means you increase your reactant concentration, but you decrease your product concentration. The question's asking you what happens to the equilibrium constant. You shift the position of equilibrium, but what was the change we imposed here? What was the factor we were changing?
Pressure.
Pressure. Pressure, concentration, volume, temperature will affect the position of equilibrium. Does pressure affect the equilibrium constant, though?
No.
No, okay. So the position of equilibrium will shift, but there'll be no change in K, because what's the only factor that changes K?
Temperature.
Temperature. Good. So that's why this is a 1-mark question. So we went through this to talk about LCP and position of equilibrium, but position of equilibrium is not the same as equilibrium constant. So that identify the change is there is no change. That's why it's 1 mark. The only factor that changes the constant itself is temperature.
Yeah.
D, nitrogen and oxygen gases are introduced into the reaction vessel and equilibrium is reached at time A. The system is maintained at equilibrium until time B, when the temperature of the reaction is increased. Represent these changes to the system at the axes provided below. Okay. It talks about adding nitrogen and oxygen gases, which normally your head tends to go towards concentration, but look at the units in the graph carefully. This isn't a concentration versus time graph. This is a rate versus time graph, which is fine. You put nitrogen and oxygen into the system, which means that's the reactant, so it's going to drive the forward reaction. So at the very start, when you put the nitrogen and oxygen in, so let's do forward for red. The forward reaction is going to start really high, and at the very start, you don't have any nitrogen dioxide product. So the reverse reaction is basically non-existent because you don't have any nitrogen dioxide colliding together.
Yeah.
And then If this was a concentration versus time graph, then the lines would just stay flat. They wouldn't have to touch, but this is a rate graph. And for dynamic equilibrium, forward and reverse reaction rates aren't just constant, they're equal.
Yeah.
And then they told you that that equal reaction rate or equilibrium happens at time A. So until then, they have to meet at time A. So that's here. That's too early. So maybe I'll start. And then, you know what I'll do? I'll adjust my starting line. That's what I'll do. And then, oh, that's forward. And then they said the system is maintained at equilibrium until time B, which means it stays flat and connected together until point B. So you just keep on going there because that's what it means for it to be at equilibrium. And then it says at time B, the temperature of the reaction is increased. Okay, now according to collision theory, when you increase reaction rate, when you increase temperature, you increase reaction rate. So both of the red and blue lines are going to shoot up. The only difference is one of them shoots up more than the other. Which rate goes up more, endo rate or exo rate? Which one's more dependent on temperature and more dependent on heat changes?
The forward. Oh,
Endo or exo?
oh no, the endo.
Endo, good. Endothermic reactions, by definition, absorb heat. Exothermic reactions release heat. So exothermic reactions don't actually want that extra heat. It wants to get rid of it. Endo reactions absorb heat. It's really dependent on the amount of heat that it has available. So endothermic reactions are way more responsive to changes in temperature. So if rate goes up, endo rate always goes up more. If rate goes down, endo rate always goes down more. But we haven't labeled this as endo and exo. We've labeled it as forward and reverse. So we need to go back to our equation and figure out which one's the endo one. So this is our equation. Is the endo one the forward or the reverse?
The reverse.
Endo's a reverse because the forward is delta H negative, which means it's exo. So the reverse is endo, which means the reverse line is the one that's going to go up more at point B. So that's what I do. My reverse line is the blue line. So all that happens is I make sure it shoots up slightly more than the red one does. And then they have to reach equilibrium eventually. So over time, they have to go back together.
Yeah.
And this is what your graph looks like.
Okay, yeah.
Any questions?
No.
All right, good. Okay, question 13. Sulfur dioxide and oxygen gases synthesize to produce sulfur trioxide gas in an exothermic reaction. A change was applied to the equilibrium system containing the reaction at time T1, producing this graph. A, write a balanced chemical equation for the reaction. We're synthesizing sulfur dioxide and oxygen. What's the formula for sulfur dioxide?
SO2.
SO2, and oxygen is O2, and they told us that synthesizes to make sulfur trioxide, which is SO3. And how do we balance this equation? Half on the O2 here would give me half times 2 will give me 1, plus the O2 will give me 3, just like it is on the right. And then if I multiply the 2 out, I'll get whole number coefficients. So this will be 2 and 2 here.
Okay.
And then once again, just to add a little bit of extra detail, they told me it's exothermic, so I'll just do delta H less than 0.
Yeah.
Part B, identify the change that was imposed on the system at time t1. All right, now, when we've done these equilibrium graph questions, we always said, oh, if it's an immediate change, this happens. If there's no immediate change, this happens. And if there's a only immediate change in one of the graphs, and this is what's happening. But that was for concentration versus time graphs. You have to read the axes carefully to see what units they're talking about. This is a pressure change.
Yeah.
Now, let's think about it. Temperature does not lead to any immediate change in concentration.
Yeah.
If there's no immediate change in concentration of the gases, then change in pressure is proportional to change in number of gases. So if you have more gases, you have more pressure. But if temperature doesn't immediately change moles, temperature should not immediately change pressure.
Okay.
So
Yeah.
you shouldn't see an immediate line up in all three graphs.
Yeah.
If this was a concentration change, then yes, if you add more gas, then the pressure should go up.
Yeah.
The only thing is, though, the chances that you add all three gases at once are very slim.
Okay.
All three gas pressures have gone up here, which kind of implies that you have more O2, so pressure of O2 went up. You have more SO3, so pressure of SO3 went up. You have more SO2, so pressure of SO2 went up.
Yeah.
Chances that you open the lid to the beaker, put all three gases in, is very slim.
Okay. Yeah.
If this was a concentration change, you should only see a change in one graph.
Yeah.
A catalyst does not give you more gases. It just makes the reaction go faster with the existing number of gases. So that should lead to no shift in the position of equilibrium whatsoever. Um, so your change here is going to be a volume change. If
Okay.
you change the volume, even though you've kept the number of gases the same, they're now moving in a more restricted area, all three of the gases. So then all three of the gases exert more pressure.
Okay. Yeah.
So it's not that there's more gases, it's that you've decreased the space that all of the gases are in.
Yeah.
So it's not that there's more gases exerting force, it's that it's the same number of gases that have a smaller space to move in, so it's more likely to hit the walls that way.
Okay. Yeah.
So, like, if you have a bunch of students running around, then you can either make them hit into each other more by having more students, which would be changing concentration. Or the other way you can get the students to hit into each other a little bit more as they're running around is to move them into a smaller room,
Yeah.
which is what this is. So if you're affecting all three pressures at the same time, the only way you do that is if you apply a change to all three of the gases at once, which tends to be a volume change.
Yeah.
And if pressure is going up, because this is a line up, if pressure is going up, then that means that the space that it's in is a lot smaller.
Yeah.
So was the volume change an increase in volume or a decrease in volume?
A decrease
A
in volume.
decrease in volume. So it's going to be B. It just asks you to identify the change. So part B is going to be a decrease in volume. If this was an increase in volume, the gases have more space to run around. They're less likely to hit into each other. So you should see a drop down in pressure, not an up.
Okay. Yeah.
Part C, explain the change in the graph after time t1 using Le Chatelier's principle. So we already know what caused the initial change. They're asking you for what happens over time. So what happened was we decreased volume, which led to an increase in pressure. So according to LCP, the system will want to decrease pressure. Pressure is caused by gases. The
Yeah.
system decreases pressure by shifting to the side with less gases. We wrote the equation in part A. Is the side with less gases the left side or the right side?
The right side.
The right side. So the system's gonna shift to the right, to the side with less gases, which means you get a lower if you're shifting to the right, you make less of the stuff on the left. So you have lower moles of SO2, lower moles of O2, if you make less of certain gases, then the pressure of those gases goes down. So pressure of SO2 goes down and pressure of O2 goes down.
Okay, yeah.
And then likewise, if you're shifting to the right, you make more of the stuff on the right, which means the pressure of SO3 goes up,
Yeah.
which is what this graph shows. So SO3 goes up, whereas O2 and SO2 goes down.
Okay, yeah.
Any questions?
No.
All right. Question 14, the following graph shows the forward bolded line and the reverse dashed line for a reaction at two conditions, condition A and condition B. Distinguish between the two conditions, justify your answer with reference to collision theory. Okay, so this is condition A and this is condition B. What's the difference between A and B?
The rate at which they reach equilibrium is
Yeah.
different.
Yeah, so they reach equilibrium at the same time. It's just that one happens faster than the other. So what might cause the reaction to go faster?
A catalyst
Y-
or
Yes, a catalyst?
something like temperature, maybe?
Yeah, it could be a catalyst, could also be uh I'm just trying to think if a catalyst would also make equilibrium get reached earlier.
Hmm.
Mm. Yeah, so let's go temperature.
Yeah.
Could it be a catalyst as well? Lowers the activation G barrier means they reach it at the same time. Let's go with temperature for now as our safe answer. Catalyst is also possible.
Okay, yeah.
So let's go temperature. Condition A, higher reaction rate, which means the condition A leads to a higher reaction rate, which could possibly mean that the condition is that A is at a higher temperature. And the question wants you to justify your answer, which means explain why you say that with reference to collision theory. So when it's at a higher temperature, you supply heat to the particles, which is thermal energy, but thermal energy is not what the particles use. The particles use kinetic energy. So this transforms into higher kinetic energy, which means more particles have enough, more particles can overcome the activation energy barrier. And the reason why I link to activation energy barrier is because that's what collision theory talks about. Collision theory talks about colliding with the correct molecular orientation and colliding with enough kinetic energy to overcome the barrier. So I want to include the words of my definition in my answer. To overcome the activation energy barrier and therefore increase reaction rate.
Yeah.
And then if we were to talk about catalyst, then you talk about how having the catalyst in condition A means that it's found a alternative pathway with a lower activation energy barrier, in which case you don't talk about the particles having more energy. The particles have the same amount of energy, but the barrier that it has to get over now is lower. So more particles can overcome the lower barrier and the rate goes up that way.
Yeah.
Any questions?
No.
All right. 15. Nitrogen monoxide and oxygen gases synthesize to produce nitrogen dioxide according to the following equation. 2NO plus O2 turns into 2NO2. Delta H is negative 62. Two changes are imposed to the system at equilibrium at separate times from each other, and the following graph is produced. Explain the changes in the graph. This is a 5-mark question, so I want to structure my response carefully. Once
Mm.
again, when you're reading these questions, we're used to rate versus time and we're used to concentration versus time graphs. This is different. This is a pressure versus time graph.
Yeah.
But pressure is related to moles and moles is related to concentration. So we can use the rules we had for concentration versus time graphs to apply it to here.
Okay. Yeah.
First change imposed. 5-mark questions, so I want to structure my answer carefully. I'm going to use the words of the question as much as possible to structure my response. So I'm going to go first changed imposed, second changed imposed. The first changed, are there any immediate changes up or down?
No.
No. If there are no immediate changes, what must the change have been?
Um,
Temperature, concentration, volume, pressure, catalyst.
Temperature.
Temperature. If there are no immediate changes, then it's a change in temperature. And then that's not good enough though, because I have to tell the mark if it's an increase or a decrease. Usually the immediate change only tells you what the factor was. It doesn't tell you how the factor moved. So we know it's temperature. I just don't know if it's an increase or a decrease. So I figure out the increase or decrease by LCP, which is the gradual change.
Yeah.
So over time, NO2 goes down, O2 goes up, and NO goes up. So looking at this equation, if NO and O2 went up and NO2 went down, did the position of equilibrium shift left or shift right?
Shifted left.
Shifted left, good. Now the forward reaction is exo, shifting left is the reverse reaction, which is
Ender.
endo. So what was the system trying to do if it liked the endo reaction?
Absorb the heat.
Absorb the heat. So what was it trying to do to temperature?
Decrease temperature.
Decrease it. Which means what did we do to temperature then?
Increase temperature.
Good. Yeah, so our first change imposed was that there was an increase in temperature.
Yeah.
So we identify the factor first. So we'll tell the marker no immediate change, which indicates a temperature change. And then we want to talk about the direction over time. So over time, so let's go gradual change using our terminology. Gradual change is there's an decrease in NO2, oh, pressure, but pressure is directly related to moles anyway. So pressure of PO2, and there's an increase in pressure of O2 as well as NO. This indicates a shift to the left, which favors the endo reaction that absorbs heat.
Yeah.
That absorbs excess heat. And the only reason the system would do that is according to LCP, it must be counteracting an initial increase in temperature and heat, which is how we know that's what the change was.
Yeah.
And then second change, do we see any immediate changes up or down?
An immediate change down for NO.
And for NO only, good. So if it's only an immediate change in one graph, is that a volume change or is that a concentration change?
A volume change.
Is it a volume change? It's a concentration change if you're only affecting one. If you change the volume, you will change the concentration and pressure of everything in the beaker because volume changes affects everything in the beaker.
Yeah.
Because you can't selectively change the volume of one and not the other because they're in the same vessel.
Yeah.
So if it's only a change in one, then it's a concentration change. So we just need to know if it's an increase in concentration or a decrease in concentration. You told me it's a decrease in the pressure of NO. Pressure is directly proportional to moles and concentration. So if NO is exerting less pressure, there must just be less NO in the system.
Yeah.
So there's been a removal of NO from the system. And we know this because the immediate change is that there's a decrease in the pressure of NO.
Yeah.
The question asks you to explain, the question doesn't tell you to explain initial or gradual. It says changes in general. It's a 5-mark question. So you want to identify every change in the graph, which means gradual change. The system, gradual change is the concentration of the pressure of NO goes back up, as does the pressure of O2, and then the pressure of NO2 goes down. And this makes sense because we said if it removes NO, the system's going to try to make it again.
Yeah.
So according to LCP, system counteracts the decrease in the pressure of NO by shifting to the left to make more of it.
Yeah.
Okay, so 2.5 marks for change 1, 2.5 marks for change 2.
Okay, yeah.
Any questions?
No.
All right. Question 16. The following reversible reaction occurs in a 1.5-liter container. Ag plus Bg turns into 2Cg. The equilibrium concentrations at 200 are 0.23 and 0.5. How many moles of A must be added to the container to increase the concentration of C to 0.7 at 200? Okay, now this one's a little bit interesting because we've told you before that if they've given you all of the concentration at the same time, then you can sub it straight into the equilibrium expression.
Yeah.
But then the question also asks you how many moles of A must be added to the container to increase the concentration of C to 0.7.
Yeah.
So when it says something like this, to change the concentration of something to get it somewhere else, the only concentration that's stable is when it's at equilibrium.
Yeah.
So when it says, don't get confused when it says, oh, C is 0.5 and then you want C to go to 0.7. All that means is that when you do set up your new ice table, the concentration of C is 0.7.
Yeah.
It doesn't mean that the change was 0.7.
Okay, yeah.
Yeah. So the change here is, with a question like this, it's easiest to think about it in terms of a graph. So what it's basically saying is 0.2 for A. So this is A, C is 0.5, and then B is somewhere up here. And then the question is saying, oh, we want to get the C concentration of 0.7, which is somewhere here. So then it goes up like this.
Yeah.
The question says, how many moles of A must we add? Which means the immediate change is a change in A.
Yeah.
And then over time it goes down. And then B goes down over time.
Yeah.
Now, these numbers at the start here, the 0.2, the 3, and the 0.5, that will give you a value for K.
Yeah.
When you set up your ice table, notice how the immediate change was only on A and not on B and C. So when you go to set up your ice table, initial concentration of B and C will be the same,
Yeah.
but your initial concentration of A is going to be the 0.2 plus whatever you have to add.
Okay, yeah.
Yeah. So when it says, oh, how many moles of A must we add? The how many moles of A must we add is not going to be in the C column of your ice table. It's going to be in the I column.
Okay.
Yeah.
Yeah.
Because when we talk about change in an ice table, we're talking about this gap.
Okay.
Yeah.
Yeah.
So I want you to keep in mind when we do ICE in an ice table, when we talk about change, that's the gradual change, not the immediate change.
Okay. Yeah.
This immediate change here, you have to figure out yourself from the initial row of the ice table.
Yeah.
Yeah. So when we talk about change, we're talking about gradual change. So when the question asks you, oh, how many moles of A do we have to add? That's the new initial. That's not the change in the ice table.
Okay. Yeah.
Yeah. So you have AG plus BG turning into 2CG. You have I, you have C, you have E. The question says we want to get to 0.7 for C. So that's the new equilibrium.
Yeah.
And the initial for C was this, that 0.7 is the new equilibrium. The initial for C is the end of the previous equilibrium, which is the 0.5.
Yeah.
And B also wasn't affected. So the initial for the new equilibrium is also going to be the end of the first equilibrium, which is 3.
Yes.
And then A is the one we don't know. The new initial for A is going to be the equilibrium plus this X that we're looking for.
Yeah.
Yeah. So that's going to be the end of the first equilibrium plus whatever your immediate change is.
Yeah.
So that's actually what we're looking for.
Okay.
And then, so notice how the change is not the X that we're looking for A. The change is actually that shift in C, which is plus 0.2.
Yeah.
And then it's a 1 to 2 ratio. So B is going to be minus 0.1. And then A is going to be minus 0.1.
Yeah.
So for A, 0.2 plus X minus 0.1 gives you 0.1 plus X. And then B gives you 3 point, oh no, not 3.9, 2.9.
Yeah.
Okay, so your takeaway from this question is the C in your ICE table is the gradual change, not the immediate change. If they talk about adding something, then that's a shoot up. That
Yeah.
thing that you added is the new initial.
Okay. Yeah.
Yeah. So when the question asks you, oh, what change do you impose? That's actually not the change in the ICE table.
Yeah.
That's the new initial.
Okay. Yeah.
Yeah, so it's easier to think about it in terms of the graph and then translate it to the table after. So then if I'm looking for X, I actually need to know what my equilibrium constant is. Otherwise,
Yeah.
I can't solve for X, which is why they had to give you all of the concentrations for the previous equilibrium.
Okay. Yeah.
So K is C squared over AB, which is 0.5 squared over 0.2 times 3. So what's the K value?
Uh, 0.416.
0.416. So that's going to be the K value at any time, particularly because they told us the change that we're imposing is we're adding A into the system, which is a concentration change. So the equilibrium constant does stay the same. If this was a temperature change, then you wouldn't get a question like this anyway, because the equilibrium constant would change value.
Okay. Yeah.
So 0.416. So for me to solve for X, I set up my equilibrium expression again. K is C squared on AB, and that's 0.7 squared over 0.1 plus X times 2.9, which is equal to the K value we figured out for the previous equilibrium.
Yeah.
0.416. And that we rearrange this to get X. So times the 2.9. So let's go times the denominator out first. 0.416 times 0.1 plus X times 2.9. Divide the 0.416 and the 2.9 over. So 0.1 plus X is 0.7 squared on 0.416 times 2.9. And then I'll minus my 0.1.
Yeah.
So what do we get for X?
0.3.
0.3 molar because we subbed concentration into our ice table. The only issue is though the question doesn't ask you for concentration of A added. The question asks you for moles of A added. How do I go from concentration to moles?
Concentration times volume.
Yes, and then they gave you volume at the start. We hadn't looked at that number because we didn't need it yet. So they actually did give you the number you need for your answer. So moles of A added is going to be this change that you added in terms of concentration, 0.3 molar times the 1.5 liters. So how many moles did we add?
0.458.
0.458 moles. Okay. So your takeaway from here is from the initial to the equilibrium is what you're setting up your ice table for. Yeah.
Yeah.
So that's why when we first did concentration versus time graphs, we said that the change is from the end of the immediate change to the new equilibrium here.
Yeah.
Because what some students did when we were first doing module 5 was they took this and then they went to the new equilibrium. You see where the line ends, and that's your new initial for the new ice table.
Okay.
Yeah, which is why that X term that I'm trying to look for A, the question's asking me moles of A added. I didn't put that into the C box. I put that into the new I box.
Yeah.
Any questions?
No.
Okay, good. All right. Let's get rid of